We have Team Aphrodite with us here. And so just to let you know about Team Aphrodite, so the sister planet of Earth is Venus, right? And we recently saw so many mysteries coming out of Venus and stuff. So this team of 10 rocket nerds have designed a propulsion system that takes a payload to Venus. So let's see the details about them and let's get to know more about their project. Team Aphrodite, you're up.
Good evening, everybody. We are Team Aphrodite, and we'd like to take you through a 6-week journey of our work internship. So, moving on, to give you a brief on what our mission objective, or you could say our problem statement was. So, we were given a task to design an interplanetary propulsion system that would carry a payload of our choice from Earth's orbit to the desired orbit around Venus. So, before we move ahead, I think we would all, as a team, like to express our gratitude towards a certain set of people who made this possible. Firstly, we would like to thank SSERD and their complete team for giving us this opportunity and also for teaching us a lot. Next, we would like to thank our mentor, Mr. Rakesh Mohanrangan, who was there through the whole journey, through every step, who gave us the best guidance we could ask for. We also had two external guides, Ms. Rasika and Mr. Vishnuvardhan, who helped us at times when we were all quite stuck, and our supervisors, Mr. Mahesh, and our coordinator, Mr. Tejas. So as you can see, we were a team of 10 people who worked on this mission. Our team leader was Dhrumal Pataria, and our assistant team leader was Rachel Rubin, both of whom were part of the systems engineering subsystem. To give you a brief about our project timeline of 5 to 6 odd weeks, the first week went on in our introduction to SSERD and us learning about the organization. The second week, we were split into our respective teams, in which we chose our team name, our logo, and finalized on our mission objective or the problem statement. Week three was when our work really picked up. We had to decide on our payload, did our delta V calculations, and also selected the propellant that we were going to use for the rest of the mission. From week 4 was when our complete work started. We had split ourselves into 4 different subsystems, which were systems engineering, feed system, tank design, and engine design. Moving forward, the first task that was given to us was the payload selection. As in the problem statement, we had mentioned that payload was up to our choice. We did extensive literature study and we finalized as a team on 3 different payloads. The first being the crash landing probe. With the recent discovery of microbacterial activity in the Venusian atmosphere, the crash landing probe is designed to study this same activity in Venus's clouds. The second one is a Venus surface geology and geophysics mission. This mission is primarily designed to map the tectonic plate movements of the surface of Venus, as well as study its volcanic activities. The third was the CubeSat UV experiment, which is a CubeSat which orbits around the planet Venus and studies the UV absorbers that are present in its clouds. So once we had shortlisted the 3 payloads, we decided to do an in-depth trade-off study where we considered 3 main factors: its scientific importance, technology readiness level, and its feasibility. Once we conducted the study and got a few points, we decided to score each out of 10. And when we scored each out of 10, we got, as the CubeSat was the ideal payload for our experiment. To give you a brief about the CubeSat, in Venus's clouds, it's been found to absorb the UV radiation that's emitted by the sun and trap it inside its atmosphere, causing for the drastic environment of the planet. This CubeSat is designed to study the reason why these UV radiation is not being emitted out of the surface and rather is stuck inside the planet's atmosphere. It weighs an approximate of 180 kgs, which we've considered as our payload mass. Moving forward, we'll have Dhrumal explaining about the mission profile.
Thank you, Navneet. So for a mission profile, we basically considered a Hohmann transfer orbit from Earth to Venus. So basically the mission was for 120 days, and the next slide we are going to show the calculations. So here we have a delta V calculation where we first assumed that we started from 4 would take us to Venus, and on reaching Venus we would perform another burn to slow down and get captured by Venus's gravity, eventually getting into an elliptical orbit around Venus that would be 75 kilometers above its surface and currently 40 per second. And this also included a few trajectory maneuvers, correction maneuvers. And now I would like to ask Sudhir to describe the propellant section.
Yeah, thank you, Drumal. So before we start our research about the propellant selection, we ignored solid propellant and electric propellant, because in solid propellant the ISP value is really less, and electric propellant the thrust by weight ratio is less compared to other propellants. So by considering these parameters, among other propellants like hybrid, cryogenic, green, and liquid propellant, we decided to choose liquid propellant by considering the higher ISP value and the restart capability. So yeah, after our literature survey, these three were our finalized propellants. Actually, solar cell is not a propellant; it's a propulsion system which do not use any propellant. Solar cell is efficient than any other propellant, but its construction and working principle is really so complicated, so we didn't go for it. So even though the LOX plus LH2 has a high ISP value, the nature of this propellant is cryogenic, which will complicate the engine design. So we went with UDMH and N2O4. So by considering this property, the UDMH was really efficient than other propellants, as it has high characteristic velocity and the density is much larger than other propellants. So now Rachel will continue with staging and mass budget.
Thank you, Sudhir. So for staging and mass budget, these are the few parameters that we had to find out. The main ones was deciding on the number of stages for the spacecraft and the total propellant mass that will be required. So calculating the number of stages, we used the rocket equation. From that, we could find out the total mass of the spacecraft. From the previous research, we found out the values of delta V, ISP, and payload mass. And we use the equation to iterate the mass of spacecraft up to 4 stages. As you can see in the graph plotted between the stages and the propellant mass, you can see that the amount of fuel used for second stage is significantly less than the first stage, and then it starts to increase again. So we decided to go with 2-stage rocket. So this is the mass budget for the 2-stage spacecraft. Here we have assumed the dry mass to be 1000 for both the stages. After finally designing the whole propulsion system, we again did the mass budget with the new dry masses, and it came out to be approximately similar to what we have assumed. So we went ahead and took this and used this assumption as correct. Can you go back to the next step? Yeah. So the total spacecraft mass is 7489.2 kg and the total propellant mass is 5309.2 kg. Next, we have systems engineering. For this, the first task was to find out the thrust that would be required for a spacecraft. Usually this is done by the guidance, navigation, and control system, but since we do not have this subsystem, we decided to do a literature review of previous Venus missions. We found the Venus Express mission data from where we found the launch mass and the thrust required. We got the thrust to weight ratio as 0.36. From that, we found the total thrust to be 2760 newtons. We divided this thrust for main engine as 1960 newtons and 100 newton each for 8 thrusters. This is the propulsion system architecture for our spacecraft. It uses a gas pressure feed system. Here you can see all the components that we have used, and we have designed it in such a way that it fulfills the control, safety, and reliability requirements with as minimum components required to achieve it. Next, I would like to call Rehan to explain the feed system design.
Yeah, thank you, Rachel. So next we move forward with the feed system design. So feed system design is basically increasing the enthalpy of the propellants in the tanks since they are at a low pressure inside the propellant tanks. So this is actually achieved by pushing the propellants at a high pressure into the combustion chamber. And normally in the aerospace industry, it is done by two methods. It's a gas pressure feed system or it's a turbopump system. As you can see in the figure, the the feed system we used for our mission was the gas pressure feed system. The reason being that it's having a superior performance in spacecrafts with low thrust, and also it's less complicated than the turbopump system, because in turbopumps you have a lot of impellers and turbines involved. So yeah, next we decided to calculate the parameters for the feed system. So that included the calculation of feed parameters like the volume of the propellant tanks and the pressure required to push it. Then came the calculation of the gas parameters, which included like which gas to use and what are the thermodynamic properties of the gas. And after all these, it's all about designing the tank which is going to hold such a high pressure gas in it. Yeah. So the basic idea behind it, like we know by thermodynamics that the high pressure gases have a tendency to expand, especially in our case we'll be using a knob. So when we open it, the gas is going to expand and it's going to press the propellants inside. So using thermodynamics, the work done by the gas in expansion would actually result in the pressing of the pushing of the propellants. So by having the volume of the tanks and all, we calculated the mass of the gas required for the stage 1 and stage 2, which is 13 kgs at 313 bars and 4 kgs at 300 bars. So once we had these parameters, the next thing was to design the tank. Yeah, so with the tank, it's all about the thickness. So the thickness should be such, and also the yield strength should be such that it should withstand those high pressures. So we did a calculation for different materials, and we considered aluminum and titanium alloys because they are mostly used in the aerospace industry. And we found out that titanium 6Al4V had done our job much easier by reducing by less mass and high yield strength. So yeah, so basically this is the specification of our tank. So this is our first stage tank, which is titanium 6L4 of 109 kgs and having a minimum factor of safety of 1.3, as you can see in the figure. And for stage 2, it's 38 kgs at a minimum factor of safety of 1.4, as you can see in the diagram. So next I would like to call upon Pradikshan to elaborate on propellant tank design.
Yeah, thank you, Rehan. And so for the design for propellant tanks is basically designing a proper dimension and sizing according to the size of the spacecraft. So the fuel which we are using is hypergolic, which require separate tanks for each stage. And considering an optimal shape of cylindrical with a flat end and and another with a hemispherical end, we are proceeding it. And to provide a positive expulsion device, we are setting it up with a piston type of PMD, which prevents vortexing and sloshing. And the material which we are choosing is titanium B120 VCA, which is compatible for both the fuel and oxidizer, and gives excellent properties in mechanical and also in the compatibility. And for the design process, it's fairly simple. It began with us assuming the tank to be a thin cylindrical pressure vessel and proceeding it with it. And considering factor of safety of 2.5 and ullage volume of 2.5%, the thickness for each material has been calculated, and titanium alloy which we chosen has shown the best result. And so for each stage we have calculated volume, diameter, and wall thickness for both oxidizer and fuel tank. And we got tank mass as 131 and fuel mass as 44 for stage 1, and tank mass is 88 for oxidizer in stage 2, and tank mass as 31 for fuel in stage 2. And I'd like to call upon Monica to explain briefly about engine design.
Okay. Thank you, Pradikshan. So basically, we have to design a combustion chamber and a nozzle for the main engine of 1960 Newton and 8 small thrusters of 100 Newton each. For this design, we have considered some input parameters and output parameters. For example, the input parameters are gamma, OBF ratio, and the chamber pressure. And the output parameters are thermodynamic properties like the pressure and temperature at different points and the dimensions of the engine. We found the input values like gamma, combustion temperature, chamber pressure from the propellant data, and OBF ratio from the stoichiometry combustion equation. Uh, from these input values, we have calculated the output values for thermodynamic properties and then the mass flow rate, Mach number, ISP, and finally the dimensions of the engine using appropriate formulas. For example, for finding the length of the chamber, we have used this graph of throat diameter versus length of the chamber, which helped us to find the length of the chamber. The following calculations had to be performed in order to find the output values. Okay, this is the list of our output values for the main engine, which has ISP of 310 seconds and Mach number of 5.15. So in this table, we have listed out the output values for our smaller engines having a thrust value of 100 Newton each. So the total mass of these small engines are that we have got is 406.528 grams. I'd like to call Navneet for concluding this presentation. This is a SolidWorks diagram of our main engine, 3D.
So to conclude our 6-week internship and this presentation, I think we as a team can confidently say that we have successfully designed a propulsion system to Venus. Our spacecraft is a two-stage spacecraft weighing a total of 7489.2 kilograms, carrying propellant of 4,500 odd liters. The spacecraft will be generating a thrust of 2.76 kilonewton and will carry a payload of 180 kgs. Our propellant tank is going to be pressurized by a gas pressure feed system using helium. Now, to come to the main part of our whole propulsion system, the engine. Our engine is a very efficient engine with an output ISP which is 93% of the ideal ISP and also functions with an exit velocity of around 3,137 meters per second. So this is just a few snippets of the fun time we had, as we would like to say that SSERD's internships are not only just work, but we also have a lot of fun as well and get to bond with our teammates a lot. So to sum it all up, we'd all like to say thank you as a team, and we'll be accepting questions now.
Thank you, Team Aphrodite. So that was an amazing presentation. And if anyone has any question, they can drop it in the chat box or just unmute themselves and ask. Okay, looks like you don't have any questions. Perfect.